rational expectations will assume that there is knowledge of the correct form of the model, say, so by, that agents, policymakers who have kind of know what the right form of the model is. The underlying model parameters, if they will be assumed to know, so to speak, they have knowledge about these parameters. These might be, parameters, either policy parameters of how the interest rate reacts to the inflation rate or output gap and the like. And even other primitive parameters or structural parameters for that matter. And they know that, other agents are also rational. So in a sense, it is a concept, it's like a fixed point concept that, what people expect about the future is kind of realized. So it's clearest probably when there is no uncertainty in the absence of shock. So, perfect foresight, say, so people have, know what the future realizations of, say, prices are and so on. So it's a benchmark. It is certainly useful, but pretty informationally demanding. So it is a strong notion. And so in a sense, expectations or forecasts incorporate all systematic aspects of the economic dynamics. So you may, there may be shocks and stuff which you don't know, but you kind of know overall, how to form, you do not make kind of so to speak systematic mistakes. So of course it is, it is a two-way relationship. It is an equilibrium in a kind of two-way relationship. So in a sense, in economics, as you know, that expectations, say, of inflation will influence the time path of inflation, right? So, what future expected inflation is by producers on the part of producers will impact on what today's inflation is, or future consumption, what people expect might influence how much they want to consume today, consumption smoothing behavior, say, and in turn, these expectations of inflation will also depend on the path of inflation, so to speak. So there's a two-way relationship. So the expectations themselves will influence expectations of inflation, say, so to speak, will influence what current inflation is. And at the same time, how these expectations are formed is basically based on, say, the past history of inflation, time path of inflation. So there is a kind of two-way interdependence between the two. And that's kind of what sets, I guess, economic models apart. And so in 1961, I guess John Moose kind of introduced the notion of rational expectations in the spirit of the cobweb model. And as Akil was saying, Keynes treated expectations are mostly exogenous, even though it's very useful models. We do the ISLM models, and even those terminologies are kind of still used in the new Keynesian models, even. And so the 1950s, 60s was kind of reliant maybe on adaptive expectations, where expectations depend on, say, the past, in a certain way. So that, Kagan model of inflation is one example, and there are others, like I think the expectations of Bennett-Phillips curve also was of a similar type. And in the 70s, actually, only did Bob, Lucas, Tom Sargent made rational expectations the standard paradigm of macroeconomics, So it became the benchmark. So of course, it is a very useful benchmark, so to speak. It gives us a benchmark against which we can, maybe evaluate a model as to how relaxation of some assumptions might impact on the actual outcomes. So it has generally clear-cut predictions as well. But as I was trying to say that, it assumes too much, and you might consider it to be somewhat implausible. So you might think that we need an appropriate model of bounded rationality, right? So, of course, the question is, what form should this take? So the answer, as my co-authors, George Evans, co-author George Evans would say, is that one is the cognitive consistency principle. We should kind of assume that economic agents, households, producers, and so on, should be about as smart as good economists, right? And so economists forecast, economic variables, say whatever inflation or something, as my example, using econometric techniques. So you might say that a good starting point is model these agents in the model as econometricians. So they kind of look at actual data, say, realizations of data, and then make their
just a minute.
decision. Yeah.
Your audio is off.
My audio is
off? Or is it just my problem?
No, I'm able to hear. I'm able to hear him.
Okay, good. Okay. So it's okay, right?
It's okay.
Okay, I'll continue then.
Zakir?
Zakir, it's okay?
ঠিক আছে.
Okay. So yeah, so that's the, so normally, you wouldn't, we assume that economic agents, if they have rational expectations, they have like full knowledge, complete knowledge, so to speak. But econometricians or the economists ourselves, we don't have that kind of knowledge. So we don't know the private agents, economists, the central banks know the true model. So instead, central banks employ a large number of economists as their staff. They formulate and re-estimate models. And this, of course, changes as the data on the economy emerges. So you might say that economists kind of engage in a process of learning, right, about the economy. So that's kind of the spirit of bounded rationality, which we will use here. So so that's the, so this is the theories of imperfect knowledge and learning. And kind of Nobel laureate, Tom Sargent, New York University, has worked, a lot on these issues. And so the earlier literature, kind of started in the early 90s or late 80s, really, with Tom Sargent with a paper with one of his students, Albert Marcet. And then my co-authors, George Evans, Seppo Honkafoy, have done a lot of fundamental work. And they have a book, actually, which is now outdated, like 20 years old, but it's still kind of the basic reference to use in this literature. But it was initially, this literature was more kind of applied to more like ad hoc theoretical models, maybe simple ad hoc models. So it didn't capture that much attention. But, since the early 2000s, it was, applied to monetary policies, like the New Keynesian model of monetary policy. And then, so Jim Bullard, who is, president and CEO of the Federal Reserve Bank of St. Louis. And then, I had a paper in the Journal of Monetary Economics. Then George and Sepp had another paper. So this kind of the applications of this literature to actual models of policy, which are used by central banks, also got, rekindled the interest of central banks themselves. And there were, in fact, lots of, conferences and so on, which started appearing and still does. So, and a lot of the actual people who have been associated with this literature have also, become very influential. So Jim himself, he was became the president of the Federal Reserve Bank, as I said. John Williams, another person who worked, he became the president of the San Francisco Fed, and then now he's the president of the New York Fed, the kind of the major player. And similarly, others like Athanasis Orphanides, who were governor of the Central Bank of Cyprus for a period of time, and so on. So as Ben Bernanke, so this quote, and there are other quotes, which I have produced here. She said in the NBR conference in July, kind of 2007, in sum, many of the most interesting issues in contemporary monetary theory requires an analytical framework that involves learning by private agents and possibly the central bank as well. So it's kind of gives you motivation that even policymakers got interested in this literature. So what I'll do is that, because, just the sake of the students in mind, give you a very simple example of which is ad hoc, and maybe then I'll expose you to some, results in the monetary policy model, and perhaps if I have time, maybe some fiscal policy as well. So take the model of this Cobweb model, the Muth model. So it's basically thought of, production of a single good, agricultural good, takes time to produce. So this single good with a demand function, which is dt, and so that's related to the price. So it's a negatively sloped demand curve, linear, even, and there are maybe some shocks, possibly shocks like these, and supply has a production lag. So in this case, the supply of the good is increasing in the expected price. So It's not the current price, so it takes time to produce the goods. So they form an expectation of the price, and decide how much to say produce tomorrow, so to speak. So that's why you have this notation about PTE, so this expected price. And we assume that these are again normal sloping, upward sloping supply curve and downward sloping demand curve. And there are some, maybe supply shocks, demand shocks, and so on. So if you have, so the notation PTE is really to denote that expectations need not be rational. So that's kind of, we use it standard in the adaptive learning literature. So if you have rational expectations, then you would assume that, this actual expectation is the mathematical expectation of the price formed at time t-1 last period. And if you assume identical expectations, simplicity, markets clear, supply and demand same, then you get equation 1. So if you can solve for the model in equation 1, so it shows you that the price, equilibrium price, is a function of the expected price, in this case suppliers, and it depends on this expectation by this parameter alpha, which is basically the ratio of the supply to the demand curve. And as you can see that this is minus. In this case, alpha is negative. So, we often sometimes say that, there is kind of negative feedback. An increase in expected price lowers the price of the good in this case. But you can have other types of model like the Lucas Islands model, aggregate supply model, which has the same form, but there alpha is like the coefficient will be positive, between less than 1, but positive. So, so this is a very simplest type of example. One variable, the price, depends on the expected price. So I'll illustrate what I mean by what rational expectations, and then what we mean when there is agents and learning in this context. So let me then, okay, before I do that, so I had, slide on motivating what are the general questions we hope to answer. And in this framework is that, as I already said, in economists know much less. So, and agents use standard techniques, econometric techniques. So the first question, actually, one of the reasons initially, why the learning literature became so was important, or it was in the 90s, is that people wanted to see if the equilibrium under learning dynamics would converge to rational expectations or not. So if you had a scenario where if making weaker assumptions about what agents or policymakers know, but you still have eventually agents behaving as if, they have rational expectations, what you have said that people who use rational expectations would say that, that is a justification for assuming rational expectations. So that itself, so it is a good benchmark. People will eventually learn and about this rational expectations. So it was what, kind of Lucas also said in one of his papers, for example, in the 80s. However, so that's one justification, which is fine, and however, it is to be noted that even in models when you have unique equilibrium, so, which I'll come to, it is not guaranteed that, people will converge with less knowledge to that equilibrium. So, of course, the other thing is, suppose you will have models with multiple equilibriums. So there are models in macroeconomics. Certainly when the future forecasts, forward-looking models, they very easily lead to multiple equilibrium. And then in that case, really the rational expectations story cannot really tell you, which outcome or which of these equilibrium you might be see in practice. Because it is really an equilibrium, kind of fixed points, argument that, whatever people realize is, kind of what people expect is realized, and that is it. But it's not, you cannot really ask about what happens off equilibrium, if they do not have these rational expectations, what equilibrium might be obtained. And in that case, learning can act as a selection criteria. And it has also been used as an explanation of actual data, for example. Hyperinflations, for example, in Latin American countries by Marcet Nicolini, and stagnation and so on, which I'll not discuss here because I'm kind of more interested in going in the concepts in this talk. And another way, which I'll touch on is what kind of monetary policies or fiscal policies to adopt in the presence of learning. So as I said, that the very process of learning by central bank and private sector may create new tasks for macroeconomic policy, as we'll see. And they may in fact be, as examples I'll show you, of multiple equilibrium in this, depending on the policy, interest rate policy. And the message, really front and center message from these types of models is that policy in this case, say for the central bank, should facilitate learning by the private sector or agents. Okay, so that is kind of the broad motivation which I gave you. So let me, behind what I was saying, and learning choice between possible different equilibrium, maybe explaining the dynamics and justification of irrational expectations. So let me see, this earlier, this cobweb example, which I had, we saw that the reduced form was of this form. So suppose I assume rational expectations. If I take the mathematical expectation, then on the first line, what you can find is that, the expectation is basically equal to this expression on the right-hand side. If you just solve that equation, it's a linear equation, so it's easy to solve. So expected value. So in a sense, the agents and the actual price will be that constant plus some, this shock, white noise shock. So in a sense, to form rational expectations, agents will need to know these values of mu and alpha. And recall that mu alpha are in turn dependent on the underlying slopes, structure of the economy. In this case, the underlying, say, slopes of the demand curve, supply curve, and so on. Maybe even the intercepts of these functions. So in that sense, there is quite a bit of knowledge, and everybody has to kind of coordinate, right? It is important that everybody has rational expectations of this form to be so that one can observe this form of the price, which is a constant plus some white noise. So so we have assumed agents knowing these parameters, mu and alpha. So in the learning literature, so we might say that what if agents do not know these values? So suppose if agents, instead of knowing these constant values or these parameters, they assume that the process for price is simply a constant plus some white noise. So a constant which they do not know, right? And so what we call is the perceived law of motion, right? And so that is constant plus some noise. And they can estimate this constant like an econometrician by some kind of method, statistical method, based on past prices, past prices, say in the whatever, large data sets, possibly T may be large. So if I call AT minus 1 the estimate of A at the end of a certain period, say the forecasted price is then this level, A subscript T minus 1. And the equilibrium, so if the agents perceive the law of motion in that form, they forecast the price of this form, and that the equilibrium price will be in the last line here, right? So the equilibrium price is determined by this forecasted price on this, which agents have. So this now determines the price at time t, right? And therefore you get kind of a new data point price. And so come next period, they will update their estimate of this value of A. So they have one more data point, they take, that updated estimate, they again make the forecast, and that will influence the market price and so on. So in this way, economy evolves over time. You might say that a natural estimate for this constant is like the sample mean from the past data. So, if you estimate a constant in a population mean, sample mean is a good estimator, like consistency and so on from econometrics. So sample mean of this past prices, and the question is what happens as T is very large, right? And you can show that, is that this will converge to the rational expectations equilibrium, this forecast, provided alpha is smaller than 1, and otherwise it does not. So in the example of the cobweb model, if you recall, alpha is the negative of the ratio of the slopes, right? That is negative. So it does fulfill this criteria. So we have convergence to the rational expectations equilibrium. Incidentally, in the Lucas model, also the same thing is true, that the coefficient is less than 1. It's positive, so you have convergence. So that's maybe a justification for assuming rational expectations, so to speak, that in these models, you do have convergence to rational expectations. So, so note that the theory, even though I put it as, econometrically, it's a good estimate for a population mean. The reason the literature has a tougher time in dealing with this issue is the fact that the forecasted price influences the actual price. So this is what is called the self-referential feedback, right? From forecast to the actual price. So there's this interdependence in economic models and macroeconomic models, and that makes the actually making conclusions about what happens much harder. So it's not a trivial problem. And, Marcin Sargent, George Seppo have done a lot of theoretical work in getting the results. So it's a non-trivial in that sense. So one easy way to get the results is through, which I want to just tell you, is the expectational stability or E-stability equilibrium, what is called. So this makes it much easier to analyze the learning dynamics. So here actually you look at a particular mapping and you see that, how stability of equilibrium is determined. So in this case, suppose agents have perceptions of this form, and the example of this form, constant plus Sean, white noise, and then the forecasted price in equation 2, right? And then we got the actual law of motion. So this is the actual law of motion, means how the price actually evolves over time. And that's equation 3, right? So what we have said is that, this constant A, so to speak, gets mapped onto this parameter. And that's called the mapping from the perceived law of motion, PLM for short, to the actual law of motion, which is this equation 4. So this mapping is gives a very simple cookbook recipe for looking at stability of equilibrium. So it's actually not that hard, certainly in simple models, to do. And you don't need to know all the intricate theorems which back this kind of analysis. So, you look at equation 5, this differential equation, namely the mapping minus the value, and that is what you get, equation 5. So in this case, this differential equation is simply linear, and it is stable if alpha is less than 1. It's in fact we call. So note that the rational expectations equilibrium is actually, if we solve this, set this equal to 0, is that value. So the equilibrium value, rational expectations, is a fixed point of this map. And so if this thing is stable, if this equilibrium is stable, then indeed agents can converge to rational expectations equilibrium. So note that in this analysis, I did not really talk about what happens to the recursive, the sample mean, how it evolves over time, because in principle, that is much harder, right? Because it's a time varying, generally, you can have more elaborate systems and you will have a time varying kind of, nonlinear stochastic difference equations, and that will be much harder to analyze. And so this is a very easy cookbook recipe to analyze stability of equilibrium. Okay, so this, I guess, I don't need to go. And you can,
just one question.
Sorry, not to talk about the
Hello, actually, I have a question about this equation number 5. So, this dA d tau equals to TA minus A. So, this equation number 5, when we walk about this adaptive learning thing, I generally take this dA d tau, this TA minus A as given. I analyze by instability using that. But is there any way of deriving, let's say dA d tau takes the form TA minus A? Is there a theoretical structure that, how do I get this dA d tau equals to TA minus A?
So that is a very excellent question. So I am not going, so the whole, that literature actually in the 80s, 90s actually saw, so the way it works out, you analyze the recursive, say the learning algorithm, least squares algorithm or whatever, and from there, under assumptions, certain assumptions, you kind of end up with this kind of differential equation. So sorry, I am listening. So I didn't go into any of those details, it is for students, but so essentially you can say, so I show that, if for large time t, and when things are settling down, this differential equation kind of describes, it is in notional virtual time, describes the actual learning algorithm at certain points of time. So this is, actually one has to show and it comes about from that. So I didn't do any of those details. So the time will just take given, and you can show this, and the book actually, if one is interested, I can give you the reference, which I don't have here.
I think that will be very, very helpful for me if you can give me the reference.
Yeah, I will certainly. I will give it to, and basically that's so the analysis becomes much simpler. But no, I didn't. So basically you end up with this kind of equation.
Yeah, actually in most of the books they take this and okay, this is the way you analyze instability, and we do that mechanically.
Yeah.
But I had this question: how do I get it?
Yeah.
Okay, so thank you very much. Thank you.
Yeah. So I can give you the if you are get in touch with me, I will give you the references and so on.
I'll send you an email. I'll obviously send you an email.
And in fact, in simple systems, in this system, it is, yeah, you can show it much easier. But, clearly time is limited. So I kind of wanted to more focus on the issues themselves. Yeah. Okay, I'll do
Thank
that.
you. Thank you. Thank you. Thank you.
Okay, so you can do this analysis in linear, non-linear models, univariate, multivariate models, and so on. So let me just jump. I don't want to, and of course, you can have underparameterized models also. In the example, I assume that the agents kind of know the solution for the model, so to speak. It's a constant plus some noise, but actually you could have and agents misspecify models like economists do, but you can still analyze the learning dynamics. Obviously, you won't converge to rational expectations equilibrium. So let me then just give you some results for the new Keynesian type model, which is kind of more interesting model. Obviously, it's and keep in mind this audience, I thought mostly the students, is that it's a dynamic stochastic general equilibrium model, and really it is the workhorse model, with Michael Woodford having a very thick book, kind of which is used in macro monetary policy analysis. And it has various ingredients which I will not go into, because I will just simply focus on the equations themselves, the reduced form equations, and do some kinds of interest rate rules and give you some results and intuition for the type of results one can obtain in these class of models. So households supply labor, they buy goods, money and bonds, firms hire labor, produce differentiated goods in a monopolistic competition, and the central bank sets the policy by controlling the interest rate. So what you end up is that for example, you can look at any book or even article like Clarida Gali Gertler, references which I can give, so you end up with kind of equations 6 and 7. So the first equation 6 is basically kind of the equation. So that's X is the output gap, inflation is pi, and the expectations of inflation and output gap appear in this equation. And the star is really, if agents do not have rational expectations, is what I leave it more general, because under learning that would be useful. Under rational expectations, one can drop the star values here. So so that's so in a sense, to briefly see equation 6, it kind of arises from log linearization of the consumption Euler equation. So instead of X is after imposing equilibrium, so you can think of that as consumption. So X consumption today, it depends on consumption, expected consumption tomorrow. So it reflects the consumption smoothing behavior of households, and this the first term is the intertemporal elastic substitution in consumption. So high real interest rate, the nominal interest rate is I, and minus expected inflation, the high real rates of interest reduce demand, which in turn reduces inflation. So that's the more high real interest rates encourage savings and agents cut back on consumption. And inflation, and the second equation, equation 7, is basically kind of the Phillips curve, where producers have constraints on price setting. It could be Calvo type or Rotenberg type, and so because they cannot adjust prices every period, they have certain expectations about future prices or inflation is, and that determines today's price. So you could think of that as and in today's price, they're forward looking, and it also depends on an output gap or demand, and the slope is lambda, so that's kind of the slope of the Phillips curve. So it's proxy for marginal costs, so higher marginal costs lead to higher inflation. So that's briefly the background, and these are all kind of variables are deviations from the steady state. and phi lambda are positive parameters, and and beta is the discount rate, which is between 0 and 1. So this is a model which is widely used. Clarida, Gali, Berkler have in the Journal of Economic Literature, and which on this, and there are numerous papers which use this. So the output gap depends, on future output gap, and negatively on the real interest rate, as I said. And actually, if you iterate this forwards, you can see that how not just tomorrow's, but future expectations of real interest rates or output gap will also influence today's outcomes. Similarly in equation 6 as well. Right. So, what the shocks are, I don't model, but they are shocks to either demand or cost push shocks and so on. So, what I'll do is that, suppose, so in this case, so this, to go back to section 7, the only thing, if I decide or determine, if I say that the central bank sets the interest rate in a certain way, then this is a complete system, basically 2 equations with 2 kind of unknowns, inflation, expectations of inflation, and so on. Suppose I take the simplest type of model, a Taylor type rule. So drop the constants, the interest rate responds to, say, inflation and output gap, and chi pi chi x are the coefficients. And based on that, so the private sector, based on that, then real interest rates and then inflation output are all determined, right? So in this case, so the normally, so the whether there exists, so there are 3 types or 3 classes of scenarios you might think of, and depending on the structure of the model, the economic structure of the model, you may have either, say, a unique solution. That's when we call it as a determinate. So it's locally unique, say. And so we say the model is determinate, and rational expectations people, and mostly, people applied macroeconomics would love that, because you have a unique kind of outcome predicted, right? And however, it may be that there may be too many solutions, indeterminate, in which case we say multiple stationary solutions, and there might be other types of solutions, fancier word like sunspot solutions. And it is actually the forward-looking elements in the model which can lead to multiple equilibrium. So the fact that, in this model, expectations of inflation output gap appear makes it more prone to this kind of indeterminacy. And here I have used the kind of what is called the contemporaneous data Taylor rule. But if you have future forecasts of inflation, say, appearing, which is probably more realistic, you will have even more indeterminacy. But I'll not analyze that case here. And finally, one case which I did not show is that there might be cases when there is actually no stationary solutions, in which case there's only explosive. But we are typically not interested in those kinds of scenarios. And so I'll not focus on those. So determinate equilibrium. So one is equilibrium kind of, there's a locally unique outcome. So under rational expectations, you can, so based on that, so there are techniques of doing that. So this has nothing to do with learning. It's a concept for rational expectations, whether it's unique or not. So you form a certain matrix. So you kind of decide which variables are free. Any variables which depends on expectations is free. And then you kind of, what you can say is that the determinate outcome is obtained, or determinacy is obtained, when this condition is satisfied. So it depends on the policy parameter, chi pi chi x, and this expression is more than 1, right? And so there is a nice interpretation of this. So it's the Taylor principle, as it is called. Suppose you think of a long-run equilibrium, where actual and expected inflation are the same. Similarly, for output gap, actual and expected output gap are the same. And if you think about no shocks, and if you use this in the Phillips curve, you can get this equation. So to speak, suppose inflation is, in the long run, is 1 percentage point higher, permanently higher, then the output gap, long-run output gap, is so much higher, 1 minus beta over lambda. Beta, lambda are the parameters in the model. So what? So that's the prediction from this model. So 1%, and then if you look at the interest rule 9, then you can see that if this is the interest rate rule, then if inflation in the long run is 1 percentage point higher, then the increase, and since the output gap is so much higher, the increase in the interest rate, the nominal interest rate, is equation 10, right? So the Taylor principle is saying that this is more than 1. So what is the intuition? So basically the intuition of what it is saying is that suppose suppose the inflation rate in the long run is 1 percentage point higher, then the rise in the interest rate is more than 1 percentage point, right? And so that means that the real rate of interest is increasing. So if there is a rise in inflationary pressures in the economy, not just the nominal rate of interest, but also the real rate of interest increases, and that reduces demand, reduces inflation. So you're coming back to equilibrium, kind of, so to speak. So that's the Taylor principle, and that's a very nice intuition. This is what I kind of already said. So I am not going to, what I explained. So that's so determinacy criteria is this Taylor principle. If I now look at, in this case, in the paper with Jim, suppose you allow for non-rational expectations, then you can show that the expectation stability condition, the equation we were looking at earlier, without going into the details, the same criteria is enough for stability. So even if agents are, say, learning regressions on exogenous variables and learning about the parameters in the absence of this knowledge, then they do converge to the outcome, if rational outcome, if the Taylor principle is fulfilled. So in this case, the two criteria coincide, determinacy and stability of equilibrium. So, sometimes people say that, okay, so then, the learning criteria does not have any extra bite, but that's not true in general. So let me then, let me show you the figure. So with some calibration from Woodford. So as you can see, this is the contemporaneous data. So this is from the paper. So phi pi is actually chi pi. The notation is different. And this is the vertical axis, is the response to the output gap. Horizontal axis is the response to inflation. So this shaded area, the white area kind of is the determinate and stable region. And the dark, shaded, the grayish area is not determinate and also not stable. And this is that line, kind of the Taylor principle line, so to speak. So that's one, you can easily show it in terms of a diagram figure. But suppose instead of the Taylor rule, so people say that's not realistic. Central banks do not have information on current values of inflation and output. So equation 11 says that suppose they respond to lagged inflation and output, right? So equation 11. So that's, Ben McCallum would forcefully say that that is a realistic form of interest policy rule. So in this case, clearly when the interest rate responds to past values of inflation and output gap, then you will have lagged variables appearing in the model, right? Because remember that the inflation, even though it is a purely forward-looking model, the original New Keynesian model, but if the interest rate responds to past values of inflation output, the model also will inherit these lags. So this is the example of, more general type of model. And you have this equation 12, which is called which is basically what is called the minimum state variable solution or the rational expectation solution. So if you think of Y being a vector of inflation output gap, so you have inflation output gap today depending on the past value, last period values of inflation output gap. And you have to solve for A bar, B bar, C bar. So these are the rational expectations values. So these you can solve, plugging into, in fact, the mapping from the perceived into the actual law of motion, if you solve it, will give you the solution. But of course, generally, the solutions would be multiple because, in fact, B is a matrix, remember 2 by 2 matrix in this case, and there could be potentially multiple solutions to this under rational expectations. And the determinate case will be when you have only one solution for B bar. So there is a unique solution for B bar, this lag value, which is stable, stationary, eigenvalues inside the unit circle, to be more precise. So that's the case which you obtain. So, in this case, if you assume under learning, you will assume that agents do not know those parameters, these A, B, C coefficients, And suppose they have a perceived law of motion of the form, same form. So it's still kind of, we make that assumption as a benchmark, but you don't have to generally. That, but, just in the spirit of the cobweb, that, they run, regressions of current inflation output on last period's inflation output, and they update these estimates through some learning algorithm, the least cost learning algorithm. And over time, what is the outcome you might expect? So you can again do what I did in the simple example, that, look at the stability conditions, which are much more complicated here because of the lags, right? The lags will make it more complicated. But what we look at is the figure for the same calibration. So if you look at this figure, figure 2 here, again, it's the chi-pi, the response to inflation on the vertical axis, and on the output gap on the, response to inflation horizontal axis, response to output gap on the vertical axis. So as you can see that, what you can show is that this region where inflation response is more than 1, but output response is small, this kind of grayish whitish area, that's determinate and stable. And this dark region is also, this region is interesting. It is determinate, but not stable under learning. So this time, the criteria are not the same. And this whole bunch in the white region is, you don't have stationary equilibrium. It's explosive. So, and this small gray area is indeterminate. And one can show, actually, when we saw that there are kind of 2 stationary solutions here, and none of them are stable under learning. So in this case, the values when inflation response is more than 1 and small response to output gap leads to determinate stable equilibrium, whereas if the otherwise, this dark gray issue, it is determinate but not stable under learning. So the criteria kind of depart, and the intuition, since there's not that much time, I guess, but the intuition is maybe just going to, and that what is kind of different is that if you look at the solution for B bar, which is the response to the lagged endogenous variables, inflation and output. So this is kind of the crucial thing kind of which differs. So in the nature of this solution is kind of important for stability under learning dynamics, because you will not start at the rational values. So you start in the neighborhood of these values, say, and so off equilibrium dynamics are important. And whether you converge or not will depend on kind of, in this case, these parameters, and actually really whether the Taylor principle is fulfilled or not. So in the case when the solution is determinate but not stable under learning, then you can show that these coefficients is positive. So inflation output react positively to inflation and output in the past. So what happens is that when the inflation pressures increase in the economy, the nominal interest rate does go up, but the real interest rate falls. The Taylor principle, one can show, is violated in this case. And therefore, actually in demand and output, inflation rise further because it's positive. So if inflation pressures go up in the past, they will raise current demand inflation, and these pressures worsen in this economy. So it is not stable under learning because you do not start exactly at those values. But if under rational expectations, actually, you do not ask this question, right? You somehow know these values of these parameters. And so if you know these values of parameters, you get a fixed point. So these expectations are indeed realized, and you stay at that outcome. So it is determinate, and if you focus on that then it's fine. But if you ask the question is, can agents kind of coordinate when they are learning in this decentralized fashion? You ask that question, and the answer in this case is no. So that's kind of what I was saying in these slides, what I already said in words. And on the other hand, in the determinate and stable region, these coefficients, the B coefficients in the matrix, are all negative, and the Taylor principle is satisfied. So in that sense, that is the reason why suppose there is an increase in inflationary pressures in the economy, and the nominal interest rate goes up, the real rate of interest goes up, and which pushes down output and inflation in the economy in the right direction. So those outcomes are kind of stable, in that case. So it's both, in that stable region. So that's the kind of difference. These criteria can differ, and in this case. So I guess, what I did, I'm conscious that I'm almost out of time. So I thought of, there's some recent paper with George and Seppo, which maybe, I could have also highlighted some fiscal policy things, issues, and which it's a nonlinear framework, and kind of how you can have multiple equilibrium in this kind of new Keynesian model, but we leave it nonlinear. And so there can be, kind of three steady states, and one can look at, and they're not all of them are stable under learning, and what kind of fiscal policies can do so it's a question about stagnation, really, and a possibility of stagnation as one of the steady states, and whether fiscal policy, can move the economy out of this kind of pessimistic expectation overhang into a better outcome is what we analyze here. But so that's, I thought of at least giving you some graphs and so on. But anyway, I guess I'm conscious that I'm out of time, and maybe I should just stop here, and I can refer you to the paper or later on. And that's
Parthoda, কিছু time দেওয়া যাবে কি?
Yeah, another 10 minutes, I think you can go, since we started and lost quite a bit of time in terms of technical procedure. So another 10 minutes, I think you can.
Okay, thank you. So,
And I think there's a question on.
There's a question, Siddhartha.
Yes, the small question is the way we have introduced lag in this particular model is through Taylor rule, and we analyze this stability and how it's compared to general determinacy condition under rational expectation. What happens if we introduce lag, let's say by habit formation kind of utility function? So what do we expect? What do we generally expect in this kind of stability stuff?
So so that's a very good point. Yeah. So what generally what I can say is that, I think maybe I did have, and I cannot. We did some cases in the latter paper in the Journal of Money, Credit, and Banking with Jim, I think towards the end, and but I don't recall the results. But I can kind of tell you more loosely what happens is that the more lags you have in the model, there is the bigger the chance of things exploding. There is a lack of stationarity. But what actually is, even when you have the lags, what is the key actually, which I did not introduce in this model, is if you have a lag in the interest rate rule per se, so the interest rate which is observed in practice, smoothing behavior by central banks, say. So if the interest rate responds to the past value of the interest rate, then that actually is very helpful for stability. So you can show that the Taylor principle is enlarged, that helps. And there's a different definition of the Taylor principle, which one can get. And I think that can compensate with the addition of lags through habit persistence or whatever, inflation, inertia, and so on. So that kind of is especially, higher the feedback to the lagged interest rate is helpful. And it was kind of noted by Michael Woodford in the case context of determinacy in his models, but we showed actually in the learning, actually it is even more helpful. So I cannot give you a full answer, I have to look, but generally my guess, I know that, this kind of inertia from the interest rate rule is definitely very helpful. But, generally, if you add more lags, there is the chance of more instability, but this will still be helpful. I think the Taylor rule principles would still be helpful for stability and equilibrium.
Oh, thank you. Thank you very much.
Okay, so so here actually this was so there's a interest now in a kind of a stagnation regime, so to speak, and the zero lower bound of interest rates. So what we develop is an extension of this new Keynesian model with a kind of stagnation regime. So you might have, say, pessimistic expectations, low output, below target inflation, and interest rates, right? So so one of the motivations in it, these are a few figures from that paper, is that for the US, Japan, and Euro area, So you have inflation on the horizontal axis and the policy rate, interest rate on the vertical axis. So this linear line is kind of the Fisher equation. It's the relationship between interest rates and inflation. And this solid line is kind of a Taylor type rule, which responds to future forecasts. It's a nonlinear rule. And you can see that since the, especially, this is more 2002 onwards, but certainly since the crisis 2007 on, interest rates have been very low, kind of, for Japan, it's almost entirely so, often for the US and Euro area as well. And inflation is also generally low. And if you look at output gap and inflation, output gap is mostly negative. Output is very low, pessimistic expectation output, very low output GDP per capita and so on. Output gaps are mostly negative, and inflation is also low. And the final picture with policy interest rates and output gap, which again, interest rates are stuck at very low levels, with output gap being generally negative for the different countries. In this model, actually, that's just a motivation. So we have a nonlinear model and 3 steady states, and 2 are stable and adaptive learning. And so we don't really, there is a 3rd steady state, but we don't really think things will be attracted there. But there is a tendency that you might be attracted to that steady state. So it's like a subsistence level steady state. And people have adaptive learning. And you can show that of the 3 steady state, the high steady target steady state and the stagnation low kind of steady state are stable under learning, but not the middle one. So and there are various messages you can give. So let me, so one of the reasons we did actually this was because the existing papers really had, did have some stories with multiple equilibrium, 2 steady states, but the levels of output in these 2 steady states were almost the same. So you don't really can produce, low output or kind of output gap, negative output gap. So that was our intention. So and in this framework. So what I will show you is maybe rather than look at. I'll show you a diagram. So this is kind of the expectation stability dynamics. Think of, you can look at inflation expectations and output expectations. So in this, this is the global dynamics. So as you can see that there were 3 steady states. Pi star is the target steady state. Pi L is the middle steady state. And pi S is kind of the 3rd, the stagnation type steady state. So you can look at the dynamics. So inflation expectations are along the horizontal axis. Output expectations on the vertical axis. So, you can look at certain type of learning without any shocks and so on. So this kind of gives you a global idea. And you can see that this target steady state, pi star, is stable learning. So there is cyclical convergence to the steady state. And this low pi S steady state is kind of, also sync convergence there. But the middle steady state, the pi L steady state is unstable. In fact, it is stable. There's a saddle path. So as you can see, that 2 of the arrows are going in that direction. And one can use this, and the level of output in the low stagnation one is very low. So one can use this feature, and if you just focus on the first 2 steady state, pi star and pi L, then you can look at a figure like this, which I'll explain in just briefly in my remaining time. So on the left side, I'm only putting, this are the 2 kind of the lines, which you can draw, the inflation, which was earlier we do. So it's a part of these lines, where expectations of inflation are constant and output expectations are constant. So in this case, and you have this is the star is the target steady state, and this is the middle steady state. We don't show the other steady state numerically. So what the yellow shaded region is the target, is the domain of attraction of the target steady state. So, and anything outside, so you can see that you're going towards the stagnation regime from here. And what you can show is that there is kind of quite sensitive dependence on initial conditions. So if you start from, this star, go down somewhere here where my cursor is. So if you have slightly below pessimistic output expectations, then you can go in this state and go towards stagnation. So these arrows show this direction of movement. And on the other hand, if it's slightly above this cursor, then you're inside the domain of attraction. Domain of attraction is that if you're inside that region, you will converge to the steady state. Then you do converge to the star, the steady state. So there is sensitive dynamics, and what we show is that, so it's a nice picture I thought I'd show you, and that you can have fiscal, this is without any fiscal policy or any type of monetary policy. You can have policies which can help you move to the domain of attraction of the steady state so that you converge. But it may be that there are, if the fiscal policy is not strong enough or kind of weak enough, not that strong, you might slip into stagnation regime. So you can, get various kinds of messages from this. We look at various kinds of messages in this paper that, that if there is for guidance or, levels of the inflation target and so on, that might be helpful in convergence to the target steady state. Okay, I'll end now. So just, I didn't go into any of the details, but this is a more recent paper and one can analyze fiscal policy in this framework. And look at.
Great. Any questions? We can have next, maybe. Kaushik, is that okay? Another 10 minutes?
Yeah, yes, yeah, that's fine. Yeah.
We lost quite a bit of time in terms of. Yes, Siddhartha.
Yeah, it's a small clarification is basically the way I basically work in this area of zero lower bound and optimal forward guidance monetary policy. And I'm recently exploring that this fiscal policy over here. So what I feel, how it could actually do, I think analytically it could possibly, let's say it's a higher government expenditure. I think this IS curve, I think this inverted U-shaped curve, right? We expect it shifts up, right? And it increases this area of convergence bigger. I think this is the way we should expect that the fiscal policy should work in this framework.
So this, if there is, so what we typically in the way these scenarios are explored since Hall is that you think of a temporary increase in government spending. So, it's that, it can go up for a year or 2 years or whatever. And so it's the rather than a permanent change. So you might have, so the way we do is that you might have spending go up for a few quarters or, and years, and then it comes back to the initial level. And so in that sense, the domain of attraction is still unchanged, but you can still see whether that is enough to, stimulate expectations and output expectations and say inflation expectations and push you towards the kind of this yellow
region. Mm-hmm.
Yeah. And it is not trivial because it's and I didn't later on you can introduce I did this is really without shocks. If you have shocks in the system, stochastic shocks, you can see that actually the path is also pretty stochastic. So there might be probability of convergence. You can have convergence with 70%. Not all the times, and there are shocks which might push you towards the stagnation region, and even in the favorable cases. So you do get a lot of the different kinds of results in this frame.
And as far as I can remember, basically that was my first third year paper when I was a graduate student. There's a paper of the Evans, Hughes, and Honkapoya, and they have taken a particular kind of Taylor rule where interest rate goes to zero when inflation goes beyond a threshold, and they have shown that with this kind of Taylor rule, we can actually eliminate the stagnation equilibrium, that the lower equilibrium. So what happened if we introduce both of them together? Let's say those kind of Taylor rule along with government expenditure, and we can compare, let's say, which one is actually working better to eliminate or to combat this zero lower bound kind of situation.
Yeah. So what is the paper you referred to? I didn't get that. So it's
I forget the name of the paper. It's even Hughes and Honkapoya. I think it is European Economic Review. I think that's something there. It was published.
Okay.
So they have a Taylor rule where nominal interest rate goes to zero when inflation goes beyond a threshold. And they said if we take the threshold properly, I can eliminate the stagnation equilibrium completely.
So the thing difference is that so I think probably, and there are lots of if you choose the I don't recall exactly what the result was, but I think I know what you mean. Is that if you have so what they are talking about in those papers and what is new here is that when they talk about stagnation, what you're calling is really the middle steady state. If we can still see my screen. So it's I star and IL, right? So they do not have this lower. So
they said that you can just eliminate that.
So the thing is that one of the problems with those kind of model or the original Benhabib Schmidt-Grohe rebate is that even the inflation rates are quite different. It may be 2% target here and say slight inflation here. The levels of output, if you see, is quite similar. So papers are not really able to explain why, in that sense, that why
the negative output gap.
Output is low as well, that the output is very low. And so one of the contributions here was to show that you could have a region where output is also much lower, and how you can remove it. So in that kind of paper which you just mentioned, normally if you have stagnation, without anything, you could have deflationary spirals. So deflation and things are kind of falling, things are getting worse and worse. Whereas here this really low steady state axis.
Any other question?
Thank you.
Any other question?
So if just to say that if people are interested, if they drop me a line, I'm happy to give references or even chat or at some point. I may not be that, maybe not in the next month or so because I'm teaching quite a bit, but I will at least respond to the email and kind of give you the references and so on.
Thank you. I will definitely email you.
So, Zakir, then I believe there's no further question. So, thank you very much, Kaushik, for a wonderful presentation. I mean, to me, who is somewhat challenging this literature, it looks like at least a minor deviation from rationality gives you analytically very rich and complex results that would be somewhat approximation of the reality. Thank you very much. I personally enjoyed it, and I'm sure students have learned it.
Yeah, thank you very much. I really loved it. I enjoyed this as well.
Thank you.
Yeah, I can share my slide. Yeah, I saw a question. So yeah, I can send to Zakir Moshmi my slides. But I can also give you, if you write, and give you the references and chat at another time. Yeah. Unfortunately, it could only be virtual, but but yeah, they've been much better face to face. But anyway, these are the new times we're living in.
But maybe at a better times we'll have to see more of brick and mortar version as well.
So thank you very much, both Professor Kaushik Mitra and Professor Partha Ray. I won't take too much of your time. I'll just end this lecture by reminding you that the final lecture of this series is on 12th November by Gary Dembski from Leeds University. All of you are welcome. The registration link is still open, so please use it. So, good night, all of you, and thank you once again for both attending and to the speakers and chairs.
Thank you. Bye-bye.
Thank you. Bye.